An AI model can answer a question in seconds, but creating that ability may require thousands of specialized chips working day and night for weeks or months. The strange part is that the finished model feels almost weightless. It is just software. Yet behind that software is an industrial process that consumes electricity, moves enormous amounts of data, produces heat, and increasingly influences where new power plants and transmission lines get built. So what is the hidden energy cost of training massive neural networks for something approaching global, general-purpose intelligence? The short answer is that training converts electricity into billions or trillions of tiny mathematical adjustments. And as models become more capable, the number of adjustments, the amount of training data, and the size of the computing clusters can all grow. To understand the power bill, start with what training actually does. A language model begins with billions of adjustable numbers called parameters. At first, those numbers do not encode useful language skills. The model is shown text, asked to predict what comes next, and scored on how wrong it was. An algorithm then calculates how each parameter contributed to the mistake and nudges those parameters slightly. That cycle is called the training step. Predict, measure the error, adjust, repeat. One step is not especially impressive. The scale comes from repeating this process across huge datasets while constantly moving parameters, intermediate calculations, and updates through computer memory. Most of the work consists of matrix multiplications. These are enormous grids of numbers being multiplied and added together. GPUs are good at this because they contain many smaller processing units that can perform similar calculations in parallel. But a frontier training run does not use one GPU. It may spread the model across thousands of accelerators because the parameters and all the temporary training data cannot fit on a single machine. Now the problem changes. It is no longer just about calculating quickly. Every GPU needs the correct piece of the model at the correct moment. The machines must exchange updates through extremely fast networking equipment. If one section waits for data, expensive hardware can remain powered while doing less useful work. This is one reason adding more GPUs does not automatically reduce total energy. More chips can finish the job sooner, but they also create more communication and coordination overhead. ML Commons has found that scaling up the number of accelerators can reduce training time while causing energy consumption to rise nonlinearly. The model finishes earlier, but the larger cluster may do so less efficiently. A simple way to think about the training cost is power multiplied by time. 10,000 chips, drawing hundreds of watts each, become a multi-megawatt computing load. Keep that cluster active for long enough, and the electricity adds up quickly. Meta's public model card for the Llama 3.1 family reported a cumulative 39.3 million H100 GPU hours for training. A GPU hour means one GPU operating for 1 hour. It could also mean 10,000 GPUs operating for nearly 4,000 hours when combined across multiple runs. The exact physical arrangement is more complicated, but the unit makes the scale visible. And that figure still does not describe the entire research process. Before a final model exists, developers may train smaller versions, test different datasets, reject unsuccessful experiments, tune the software, and run safety evaluations. After pre-training comes post-training, where the model is refined to follow instructions, use tools, reason through tasks, or avoid harmful responses. If you enjoy explanations that connect the software to the physical machinery underneath it, subscribe, because AI becomes much easier to understand once you stop treating it like magic and start following the energy, chips, and data. The GPUs are also not the whole data center. Servers need CPUs and memory. Storage systems hold training data and checkpoints. Networking equipment moves information between machines. Power conversion equipment changes electricity into forms the hardware can use. Cooling systems remove the heat. The International Energy Agency estimates that servers account for around 60% of electricity use in a modern data center on average. Cooling can range from roughly 7% in efficient hyperscale facilities to more than 30% in less efficient enterprise data centers. The exact mix changes from one facility to another, which is why a number based only on a GPU's rated power can miss a meaningful part of the system. There is also idle capacity. AI services need spare hardware so they can handle sudden demand without making users wait. A machine drawing power while waiting for the next request is still part of the footprint. Google's 2025 analysis of Gemini serving found that active AI accelerators represented 58% of the energy used for its median text prompt. Host processors, memory, idle machines, and data center overhead made up the rest. That brings us to one of the biggest misunderstandings in this debate. Training is dramatic, but it is not the only cost, and it may not remain the largest cost over a model's lifetime. Training creates the model once. inference. Inference is what happens every time someone uses it. A single short text request can be relatively small, especially when many requests are efficiently grouped together. But a popular model may serve enormous numbers of requests. Longer answers require more generated tokens. Large context windows require the system to process more input. Image generation, video generation, advanced reasoning, and AI agents that repeatedly call models can demand far more computation than a basic question. The IEA reported in 2026 that the energy used per individual AI task has been falling extremely quickly, with recent annual improvements of at least an order of magnitude. But it also warned that reasoning, video, and agentic workloads can use hundreds or thousands of times more energy per query than simple text generation. That creates an efficiency paradox. If one AI response becomes 10 times cheaper to compute, companies can place AI into 10 times as many products, generate longer outputs, or run agents continuously in the background. Efficiency lowers the cost of using the technology, which encourages more use. Total demand can rise even while each individual task becomes more efficient. This is already visible at the data center level. According to the IEA's 2026 outlook, global data center electricity consumption reached about 485 terawatt-hours in 2025 and could rise to roughly 950 terawatt-hours by 2030. That would be around 3% of global electricity demand. AI-focused data center consumption is expected to grow much faster than the overall total. These figures cover data centers, not just neural network training, and projections are uncertain. Hardware efficiency, AI adoption, supply constraints, and new applications can all change the outcome. Still, the local impact can be more important than the global percentage suggests. Data centers are concentrated. They do not spread their electricity demand evenly across the planet. A large facility may connect to one regional grid near one town using transmission equipment that can take years to approve and build. The IEA notes that a data center can become operational in 2 or 3 years, while major energy infrastructure often takes much longer. That mismatch creates practical consequences. Utilities may need new substations, transmission lines, batteries, or power generation. Communities may debate who pays for those upgrades. Grid operators must prepare for large loads that can change quickly. And if clean electricity cannot be added fast enough, rising demand may extend the life of fossil fuel generators or encourage new ones. Electricity use and carbon emissions are related, but they are not identical. The same training run powered by a low-carbon grid can create far fewer operational emissions than one powered mostly by coal or natural gas. Timing matters too. A data center may have plenty of renewable electricity available during one part of the day and rely on a more carbon-intensive mix later. Buying renewable energy contracts can help finance clean generation, but it does not make the physical grid disappear. A model still needs reliable electricity whenever training is running. A serious environmental accounting system should therefore show both energy consumption and the emissions associated with when and where that energy was produced. So how can the cost be reduced without simply stopping AI development? One approach is better hardware that performs more calculations per watt. Another is lower numerical precision. Training does not always need every number represented with maximum detail, so formats using fewer bits can reduce memory movement and computation. Quantization applies a related idea when models are deployed. Software can keep chips busier, reduce communication delays, and group inference requests efficiently. Sparse architectures, such as mixture of experts models, activate only part of the network for a given token. Distillation transfers some capabilities from a large model into a smaller one, and many tasks do not need the largest available model at all. Routing a simple request to a smaller, specialized system can save energy, money, and response time. Even then, there are trade-offs. Aggressive compression can reduce quality. Larger batches may improve chip utilization but increase latency. Moving workloads to follow clean electricity can conflict with user demand or data location rules. And making a model more efficient does not guarantee that the company operating it will use less electricity overall. The most important missing ingredient is transparency. When companies disclose only chip counts, only carbon offsets, or only energy per prompt, outsiders cannot reconstruct the complete picture. Useful reporting would separate pre-training, experiments, post-training, and inference. It would include the full data center overhead, hardware manufacturing where possible, the electricity mix, and the amount of useful work completed per unit of energy. The real question is not whether AI uses energy. Every digital service does. The question is whether the intelligence produced is valuable enough to justify the infrastructure, and whether that infrastructure is being designed around efficiency rather than unlimited scale. A massive neural network may live as numbers stored on servers, but its intelligence is supported by something very physical: chips, cooling systems, transmission lines, generators, and the communities around them. The more global AI becomes, the harder that physical layer will be to ignore. What part of AI's energy footprint should we investigate next? From cooling and water use to chip manufacturing, or the power cost of AI agents? Leave your questions and topic suggestions in the comments.